Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss about some of the definitions and the terminologies related to simple stress and strains. What is resilience? Resilience is nothing but the total strain energy stored in your body is known as resilience. What is this strain energy? Strain energy means when the load is applied on the body, so there will be deformation. During the deformation, the energy will be stored. Then that energy is known as strain energy. Now, proof of resilience means the maximum strain energy stored in your body is known as stored in your body is known as proof resilience. Here, the resilience means the total strain energy stored in your body is known as resilience. It is the maximum strain energy stored in your body is known as proof resilience. Another term is known as the modulus of resilience. Modulus of resilience means the strain energy per unit volume is known as the modulus of resilience, or it is the proof resilience of a material per unit volume, that is known as modulus of resilience. Resilience is going to be studied by sigma squared by 2e times volume. That is known as sigma square by 2e times volume is known as resilience. Here the sigma is the normal stress and E is modulus of elasticity. E is modulus of elasticity. And where is the volume? The volume is length, breadth and thickness. Or the volume, the formula for volume is area times length. So here this resilience, proof resilience and modulus of resilience are terms related to the strain energy. Now, what is the meaning of strain energy? Strain energy means in a particular form, it stores the strain energy in a particular form of, it is a particular form of potential energy, which is stored in the materials which have been subjected to strain or to some change in deformation. Subjective strain takes place when you apply the load on the body. If you consider the rubber band, you apply the load in tensile direction, there will be a deformation. At that time, during that strain, it will be stored particular in the form of potential energy. There is a particular form of potential energy stored within materials. So here when the load is applied, and also strain energy means when there is during the deformation condition, the energy stored in the material is known as the strain energy, provided the load is applied, either tensile load or compressive load or shear load is applied on the body. If we consider the spring, spring, helical spring, not a spring is season, helical spring, if we consider, apply the load. If you apply the load, compressive load, then it will be compressed and stored. There is a deformation, reduction in deformation. During the application of the load at this position, the energy stored within the material is known as strain energy. Here, another definition of the strain energy means energy stored in the elastic body under loading. What is the strain energy of the material? The strain energy of the material, is also, these are all having similarity of the definitions, but in order to understand the simplicity in one sentence, what is strain energy? Energy stored in an elastic body under loading. That's what I have shown you. The spring, elastic body is one of the spring, helical springs, and when the load is applied, it will be stored under loading. Similarly, if a rubber band, if elongated under loading, under tensile load, energy stored in elastic body. And if you're sitting in a spring chair, when the load is applied, when you're sitting, after applying the load, the energy stored in the material, that is known as elastic body, is known as strain energy. Now here, the strain energy, okay, when it will be energy stored under loading, this under loading, another meaning is, under loading means there will, at that time, after applying the load, there will be a temporary deformation. During the deformation, now the strain energy definition can be spoken as, it is defined as, can be give a definition of, it is energy stored in your body or in an object during or due to a temporary deformation. Why? What is the meaning of temporary deformation? Temporary deformation means when the load is removed, when the load is unloaded, it regains its original shape. That means the body is an elastic body. So during the elastic body condition, that means in elastic body or on the elastic body, if the load is applied, the energy stored in that body, in the object, is known as strain energy. So the total strain energy stored from initial to final in your body, then it is known as resilience. So the resilience and the maximum energy stored in your body is known as proof of resilience. The maximum energy or the maximum strain energy stored in your body is known as proof resilience. So what is the modulus of resilience? The proof resilience per unit volume. Proof resilience per unit volume is known as modulus of resilience. So proof resilience per unit volume, at that time, this modulus of resilience becomes sigma square by 2e formula mathematically. Modulus of resilience, sigma square by 2e. Okay. And this total strain energy definition. So strain energy, once again, when the load is applied, what is the type of load? The load can be a compressive load or tensile load and also shear load. If the compressive load is applied, there will be deformation and reduction in cross-sectional area. When the compressive load, when the tensile load is applied, there will be deformation, increase in length, reduction in cross-section area. When the compressive load is applied, there will be increase in area of cross-section and a reduction in the length. So here, during those conditions, the energy stored in the material is known as, or in the object is known as strain energy. So the strain energy is what type of energy? It is a particular form of potential energy. It will be stored in the form of potential energy. Now here in this figure we can see how the strain energy is stored in the figure. Yes, in the helical spring. When the load is applied, okay, it will be stored in the form of, that's why because of this property of the material, the springs are used for different purposes. Here when the tensile load is applied, then on the helical spring, the energy stored within the material is known as strain energy. Now, how to calculate the strain energy? The strain energy can be calculated, that is strain energy equal to of load into deflection. That is the load F into deflection delta. This is the strain. So here this delta is deflection or compression and F is the load or force applied on the body. So when in the spring, on the spring, suppose when the load is applied W, there will be a deformation. Okay. This is known as a delta. The load applied on that F. What is the strain energy stored? The strain energy stored of times So that is the average of of times average of potential energy of times load, that is the force applied into the deflection, how much it is. Here under compression load, it is proven that under compression, if it is in tensile load, under tensile, what is the deflection? So the term for delta is deflection. Okay. Now here in this case rubber band condition is there. So here the load is applied tensile direction. The energy stored in the material is known as strain energy. The strain energy can be calculated. What is the total load applied and also what is the deformation takes place here. So that load here, very simple, 0 plus F into delta by 2. That is the strain energy. That is of F into delta. Okay, this is about the strain energy. At that time, the energy stored, the total energy stored in your body is known as resilience. What type of energy stored is total strain energy stored. So the maximum strain energy stored, what is the maximum limitation? It can store that energy. That maximum strain energy stored is known as proof resilience. So proof resilience per unit volume is known as modulus of resilience. Here tensile load is applied here. During the tensile load, the energy stored, the elastic body is considered, tensile load is applied. There will be deformation and reduction in cross section. So the energy stored during applied load, tensile load, then it is strain energy. Now, how to calculate the strain energy? Suppose here a rod of area of cross section, that is 100 millimeter square, has a length of 3 meters. This is 100 millimeter square millimeters and it is 3 meters length. Determine the strain energy stored. What is the strain energy stored? If the stress, normal stress is 500 megapascals is applied when stretched. Modulus of velocity is 200 GPa. So this is the area of cross section was given here, and one more thing is that the length also mentioned, L equal to 3 meters. Now what is the formula for this? The formula for this is sigma square by 2E times volume. The volume equal to area into length. Volume V equal to area A into L. This area is in millimeters, convert into meters. 10 power minus 3 whole square into L. This is volume. And what is sigma square by 2E? We know the formula that potential strain energy equal to sigma square by 2E times volume. Sigma square by 2E times volume, that is the strain energy. The strain energy is of load in deflection, but here another is that sigma square by 2E into volume. That sigma square by 2E, sigma square by 2E into volume, that is sigma square. What is the sigma here? 500 megapascals, 500 into 10 power 6 whole square, and it is 2 into E, 200 gigapascals, 200 into 10 power 9, 2 into 210 power 9, volume, that is area into L, 100 millimeter square, 100 into 10 power minus 6, that is 100 into 10 power minus 3, 1 millimeter equal to 10 power 100 millimeter square. Area A equal to 100 into 10 power minus 3 whole square. Then it becomes 100 into 10 power minus 6. So it is not a 10 cube. 1 millimeter equal to not 10 per cube millimeters. No, it is 10 power minus 3 meters. So it becomes 100 into 10 power minus 6. So then area, that is area. What is the volume equal to A into L? That is 100 into 10 power minus 6. What is the L here? 3 meters. This is what this total component gives, volume. This term gives sigma. that is sigma square, 500 in megapascals, 500 into 10 power 6 Newton per meter square. 2 into E, that is 200 gigapascals, 200 into 10 power 9 gigapascals. 1 gigapascal equal to 1 GPa equal to 10 power 9 pascals. 1 megapascal equal to 10 power 6 pascals. So the value is obtained here. Here it is 18.75 joules. That is the strain energy stored here. So here the rod is 100 square millimeters and length is 3 meters, and the load applied, if the stress applied on this is 500 megapascals, and the modulus of elasticity, the property of the material, that is 200 gigapascals. So the energy stored in this, the strain energy is 18.75 joules. So in that manner we can calculate the strain energy stored. So what is the stress strain curve? Suppose if you want to study the behavior of the materials, we have to the behavior of the materials can be studied by using the stress strain diagram. And here we are going to show you there are different types of materials. Mainly very important materials are, one is ductile materials, another one is brittle materials. For ductile materials, what is the property of the material? Ductility means ability to form a thin wires. So having ability is the ability of deformation. Ability of is the property of the material, that is known as ductility. So the stress strain curve for a brittle ductile materials, it will be shown. It comes like that. Is the stress on axis Y, strain on axis X. So under universal testing machine, under UTM, so the under UTM, the stress strain curve will be appeared like this. There are various points A, B, C, D, E, F. So here A is the zone A, B, C. One is the yield point here. Another one is, there are two types of zones. One is elastic region or elastic region. Another one is the plastic region. So here ultimate stress, the ultimate tensile stress. Now here it is the fracture point. F is the fracture point. The ultimate stress, E is the ultimate stress. So it's the plastic region, and within this elastic region, this is the strain. And the tensile test, we can see here the tensile test of ductile materials. The stress on axis Y and the strain on axis X. When the tensile load is applied, it is the specimen. When the tensile load is applied, there will be necking. This is known as a necking point, and after that fracture takes place. And here the tensile, again stress strain curve of another materials, tensile load is applied on this, and these are the strain gauges. The strain gauges are useful for measuring the strain. This is the normal nominal stress, it is the nominal strain, the point proportional to limit, and it is the elastic limit. The slope of this the stress strain slope equal to stress by strain. Stress by strain, it is known as modulus of elasticity. The slope of a stress strain curve gives the value of modulus of elasticity, or another name is called Young's modulus. The Poisson's ratio equal to transverse strain by longitudinal strain. Transverse strain, that is in negative here, transverse strain by longitudinal strain. So we can measure here, Poisson's ratio can be measured by using this even from tensile testing experiment, that is UTM, universal testing machine. From that we can measure one of the elastic constant, okay, by knowing this Poisson's ratio. After knowing the Poisson's ratio and modulus of elasticity can also be measured from this stress strain curve. We know E and we know the Poisson's ratio mu. So if you want a relationship between EC mu, then E equal to 2k times 1 plus mu, like that we can see the relations we can find out, and the other elastic constants can also be calculated. So there are various types of elastic constants. The elastic constants are, one is the Poisson's ratio, mu, another one is modulus of elasticity, modulus of rigidity, it is denoted by G, and it is K. So the relation between EGK, E equal to 9 kg by 3k plus G. This is the relation between EKG. That means modulus of elasticity, bulk modulus, and modulus of rigidity. These are the relations. So from this we can calculate bulk mod G, modulus of elasticity, modulus of rigidity can be calculated, and also modulus of elasticity. Bulk modulus can also be calculated from this. So after knowing bulk modulus of elasticity and Poisson's ratio, we can calculate EK mu relation. By using EK mu relation, K can be calculated. Another one is EC mu or EG mu relation, G can be calculated. Okay. So this stress strain curve is so important in order to study the behavior of materials. And how the stress strain curve for brittle materials. In the brittle materials, we can see here direct fracture. The stress strain curve indicates the brittle materials stress strain curve. So if we compare the stress strain curve of both ductile and brittle, or both brittle and ductile materials, it looks. So here the stress strain curve, the brittle materials and the ductile materials, how the area. So the stress and the strain, it looks the ductile materials having the proportionality limit, elastic limit, proportionality limit, elastic limit, yield point, ultimate, and fracture. Whereas in brittle, direct fracture only, the brittleness, the straight linear, there is no permanent deformation. So, but there is a limit where here the brittle materials, the curve, stress strain curve looks it's like a straight, there is no curvature. Here, whereas the ductile materials, it is a straight line, then it goes. That means ductile materials are having capability of what? The deformation. So, whereas brittle materials, no deformation, directly breaking. Now, various types of loads. One is very important to understand the concepts of strength of materials. So, one type of the load is the tensile load. If the tensile load is applied, another type is compressive load. Third type is shear load. Fourth type is torsion. And final one is bending. So here the types of loads, the compression load is applied means when during the compression load, these are the five fundamental types of loadings. These are the types, combinations maybe, not like in practical application, these combinations will applied. These loads in combination, not compressive load only applied on the body. No, it can be compression and tensile, torsion, bending, and also shear. All these combinations will occur on the body. Now here, when the compressive load is applied, what will happen? There will be reduction in deformation, reduction in length, and increasing area of cross section. During the tensile load is applied, during the tensile load, deformation, increase in length, reduction in area of cross section. Shear load, breakage, shearing. Torsion also torque takes place with the rotation load. The bending takes place. Bending also, during bending is a 3-point bending. What will happen? On top layers, when it is bending like this, suppose the beam, apply the load, point load, there will be a bending position up because of this. Because of this, what will happen? Inside, compressive stresses will be developed, and outside of the layers, that is a tensile stress sigma T. Now tensile load. This tensile load, there is a deformation and reduction in cross-section area, and finally it crosses the limit, then fracture takes place. During the compression load, increase in area of cross-section and reduction in deformation and reduction in length. And if you consider the shear force, there will be deformation. How the shear force is acting parallel to the cross-section. And the case of torsion, you can see the torque. Fix it one end and you are applying that circular load. So the torque, because of the torsional load also, there will be a failure in the material. The torque. During the torsion, the direction of when the load is here, the torque in the direction of the torque will be here, in this direction. So, and finally bending load, you can see in the bending load. In this bending load on the top layers, the compression stress will be developed here, sigma C, and outside of this is sigma T, tensile stress will be developed. So bending, because of the bending also there will be a deformation. Deformation can be taken place. So there are various types of the loads. One is point load, another one is uniformly distributed load, and another type of load is uniformly varying load or triangular load. Now we can see all tension, compression, shearing, torsion, bending, and one more is known as buckling. This buckling takes place especially in poles or beams, and also aircraft wings. The buckling, because of this buckling load, you can see when the load is compressive load is applied, the bending is the buckling, reduction in length. So here bending also takes place. Here the due to torsion there is a twisting, that is called vibration. This is a torsional mode. Because of this torsional mode there will also failure. Shearing, because of the shearing load, the shear force which is acting, there is a damage. Here these are the all types of here not only along 5 types of loads, but there is one more also buckling. So these are the way, but in practical not one after another will occur. All combinations will occur according to the application of the load. If the tensile load is acting there, tensile is immediately compressive. The combination of tension and compression and the shearing. So we have to design the component in such a way that while designing the component, we have to consider what type of load are being acted on the component, considering those loads such a way that the component can have more strength for that particular loads. Okay, next. So if we want to find out the relation between elastic constants, the elastic constants are mu, E, G, K. These are the 4 elastic constants which are very, very important. So mu means that's the Poisson's ratio. The Poisson's ratio is transverse strain by longitudinal strain. So here if we want to know the relation between E, K and mu, so then E equal to 3K times 1 minus 2 mu. E equal to 3K times 1 minus 2 mu. This is the relation between E, K, mu. Now there is another constant E, G, mu. If you want E, G, mu, this E, G, mu relation means E equal to 2G times 1 plus mu, not 1 minus 2. E equal to 2G times 1 plus mu. Here mistake is there, 1 plus mu. And E equal to another relation, E, G, K, E equal to 9 kg by 3K plus G. E equal to 9 kg by 3K plus G, or G plus 3K. So these are the relations, various relationships among various elastic constants. Next, these are the references we followed. Next, what is meant by a shear force diagram? Here it comes under the some of the definitions related to module 2. That what is this shear force and bending moment diagrams. So here the shear force diagram is nothing but in order to study the variable shear force along the length of the beam. That diagram is known as the shear force diagram. So from this shear force diagram, we can study the behavior of the material during the loads, especially on the beams. When the load is applied, how the shear forces variation is taking place throughout the length of the beam. Okay, from the diagram we can understand the effect of the loads on the beams such a way that we can design or we can construct the optimum or enough strength, optimum beams can be designed from this shear force diagram. So the shear force diagram is so important, especially in civil structures or buildings construction or bridges construction. So another is known as the shear force and bending. The short form of shear force diagram is SFD. What is the SFD means? S indicates shear, F indicates force, D for diagram. Shear force diagram. What is BMD here? It is the bending moment diagram. So it is a bending moment diagram. That's why here it is the shear force and bending moment diagrams. As I explained here, shear force diagram shows the variation of the shear force along the length of the beam. Similarly, bending moment diagram means shows it shows the variation of a bending moment along the length of the beam. That is known as bending moment diagram. Now, what are the types of beams? There are various types of the beams. One is, we can understand that continuous beam here. A continuous beam is the one that has two or more supports to reinforce them. Another type of beam is a simply supported beam. The simply supported beam having supports at both ends of the beam. And fixed beams, overhanging beams, cantilever beams. These are all the beams very important for constructing any buildings or bridges. So here fixed beams means both ends are fixed. Overhanging beam. The overhanging beam means one end will be extended. This is the overhanging beam, either left side or right side or both sides. This is the overhanging beam. Cantilever beam means fixed at one end and free at the other end. Fixed at one end and the free at the other end. This is the cantilever beam. This is the cantilever beam. Now here, the cantilever beam looks like that, and this is another beam that is called simply supported beam. Here there is supports, cantilever beam, and is fixed completely. In the case of simply supported beam, here there are different types of supports. Here it is a knife edge support. Both are knife edge supports. And the case of overhanging beam, it can become either left side overhang. It is exactly fitted here, then means up to this portion it is a simply supported extension, is known as overhanging. And it can become a not only left side, both the sides also overhanging beam. The next type of the beam is known as the fixed beam. Both ends are fixed. Whereas in cantilever beam, one end is fixed, another end is free. In the case of fixed beam, both ends are fixed. If the cantilever beam fixed both the ends, then it is known as a fixed beam. Cantilever beam is always fixed at left or right side. Only another end should be free. Then it is known as cantilever beam. So in the case of in the buildings, there will be balcony. In the balcony, if you see, supported by a beam, is known as all are cantilever beams. Here is the wall, support beam, and this beam here extension wall, compound wall. This is known as the beams used for that balconies is cantilever beams. And another type of beam is the continuous beam. The number of supports are more than 2. If the one of the support is removed, if the middle support is removed, it becomes simply supported. If you remove either left side support, extreme left support, then it becomes overhanging beam. If you remove extreme right side support and remaining 2, if we keep it here, these 2, if you remove this, then it also overhanging beam. But if you remove the middle one, then it becomes simply supported beam. So in this continuous beam, there are more than 2 supports. So these are the types of beams. Next, coming to point loads. This is the point load means there are types of loads. Point load is a force applied at a single infinitesimal point at a set distance from the ends of the beam. That is the point load is a point load is represented, suppose if we are considering simply supported beam. What is the point load and the simply supported? This is the point load. Point load is represented by either up arrows or down arrows. This is the point load. So it is infinitesimal point at a set distance from the ends of the beam. What is the distance from this x? From this distance y. So from ends at a distance it acts. But what is the point it acts? It is single infinitesimal point. The force which is acted P. Then it is for point load. So point load, another name is also known as concentrated load. The point loads, these are the various point loads, W1, W2 and W3. These are the various point loads are acting on the beam. So what type of beam here? It is the roller support one end and another one is also roller supports. Both are roller supports. Two roller supports are there here. So here to show the type of load, point load. Here it is uniformly distributed load. The uniformly distributed means it is another name of uniformly distributed load is known as rectangular load. It is represented by like this uniformly distributed load. It is acting on the beam. And one more thing is that it is also rectangular load. If you draw a rectangle, so W Newton per meter, suppose it is acting for 4 meters. So per meters, W Newton per meter for 4 meters, 4 Newton per meter times 4. That is 4 W it is acting. Where it will act rectangular, passing through the centroid. So another type of load is known as uniformly varying load. It is also known as a triangular load. The triangular load. The variation acting. These are the loads symbolism presentation. That is a uniformly varying load. Okay. These are the types of loads again. One is point load. Another one is uniformly distributed load. And third one is uniformly varying load. Next here, the combination of all loads at one place here is a point loads or W1, again infinitesimal, concentrated on the beam. And how can we know location? Either from left side or right hand side. The locations of the loads we can see it. So this is uniformly distributed load and a uniformly varying load. The point load, another name is known as concentrated loads. And uniformly distribution load, another name is called rectangular load. Third one is uniformly varying load, is a triangular load. So what is the total load acting? The total load is acting means is like a triangle of base into height. That volume, the area, the total area. This of base is the B and height. This is, and where it acting passing through it, the CG of this triangle, center of gravity or centroid of this area. So we have to use centroid here, is the plane. Now whereas for rectangular load, the load is W here, Newton per meter. The area of this rectangle is known as total load. Area of the rectangle, what is the total load? You consider it this total length multiplied by W. Then total will come. Suppose it is the L is there. So W times L. WL is acting. Total load. Where it will act through? Passing through the CG. That is L by 2 distance. WL is the total load. Now we have to convert this UDL, uniformly distributed load, and UVL into total load, and we have to consider the total load where it is passing through. The location of the total load is the centroid of the particular load. If it is a rectangle, half of the length. If it is triangle, we can see that h by 3 and 2h by 3 distance. We have to consider it. Now, coming to the sign convention, in the case of sign conventions. The sign conventions are very important in order to draw the SFD and BMD. That is shear force diagram and bending moment diagram. For that, these sign conventions are very, very important. Then only we can observe the variation of the shear force from left hand side of the beam to the right hand side of the beam, or from right hand side to left hand side. Similarly, variation of the bending moment also can be observed in bending moment diagram by using these sign conventions. So here, if it is a tension means positive and compression means negative. Whereas for shear force, for the pure shear is acting, the tensile means clockwise portion. Clockwise means clockwise. This is the right side, left side should be upwards, it is the positive, and right side of the section is downwards, it is positive. So similarly in opposite direction, it is in counterclockwise direction. That means left side is downwards and right side is upwards, it is a negative shear. And bending, whereas for bending moment sign convention, upward movement, that is called bending, is the positive bending moment, downward is negative bending moment. So positive and bending moments are another names are also here, hogging and sagging. This is the sagging position and it is hogging. So sagging means like when the rope, when you put the cloths on the rope, then it will sagging. So the sagging considered as a positive and hogging is considered as a negative. But the direction here it is, you have to understand the why it is in rotation motion, that is the moment, force into distance. This force into distance causes to rotate, to bend. Then it is another bending moment. The variation of the bending moment can be studied throughout the length of the beam by using, or the variation of the bending moment values can be calculated by using these conventions, these sign conventions. So the sign conventions are very, very important in order to draw the SFD or shear force diagram and bending moment diagrams. Now here, suppose in this slide, here there is a simply supported beam. This is the simplest type of beam is simply supported beam. It is a simply supported beam. For this simply supported beam, the load is applied here, it is point load. When the point load is applied, the shape of the shear force SFD will be like this. So, how the shear force is varying here? The shear force is positive up to half of the length. This portion it is positive. And the next portion it acts as a negative shear force. Negative shear force means positive shear force and negative shear force. So this positive shear force causing here half of the, but point load is applied P. And the shape of the bending moment diagram is linearly varying movement. So it is the positive completely bending moment. Okay. And again, here the load applied here it is uniformly distributed load, UDL. UDL is acting. When uniformly distributed, what is the type of beam? The type of beam is again simply supported beam. The type of supports here it is a roller support and here it is a hinged support. Now hinged support means should be here it is a, we can say it as a knife edge support. Okay. For that, when the beam here for the knife edge support, what is W here? That is Newton per meter. The shear force diagram SFD can be observed for UDL variation. Now here in the before, when the point load is applied, it is a constant. Why it is a constant? The load variation, shear force is a constant. That's why it is constantly it is acting half of that. Again it is constant in negative direction. Now another one is called here linearly varying. Why UDL is varying? If we consider the equation here F and the distance X, what is the shear force here? The load is acting W. So it is proportional to linearity varying. That's why linearly varying. Now here coming into the quadratic. That's why the equation bending moment. Now these shear variations comes from the parametric equations. Those parametric equations already mentioned in the previous sessions. From those sessions, you can see the shape of the curve will be varied. Now, here another one. The third case is a fixed beam. Here is the fixed condition. In the fixed condition, the point load is applied. So, here what type of load is acting here again? For SFD, it is again constant. And whereas for bending moment diagram, it is varying positive from part of the length of the beam, and again part of the length of the beam is positive, negative part of the beam, another part of the beam is bending moment is positive, and another one is negative. Positive, what will happen, this positive and negative, because of this positive and negative, the bending moment, because of the positive and the negative, yes, positive means sagging portion, here how it is, negative means again hugging. So this positive portion, it will be like that bending. Positive portion, suppose it is negative portion here, like that, positive portion becomes again negative portion. So the stresses this, because of the bending moment of, the effect of this bending moment, this point load, how even though it is point load on the center of the beam, but the effect is positive in the middle and the negative at the extreme ends. There is negative bending moment. So to maintain, but the stress, SFD, shear force is acting, the positive off again negative. So the effect of the direction of the shear force, even the load is applied, only applied vertically downwards, but the effect inside the beam is entirely different. This analysis is known as bending BMD analysis or SFD analysis. So the variation, shear force analysis and bending moment analysis. So to find out throughout the length of the bridge, suppose if we consider the bridges, so there will be more than 2 supports will be there, number of supports. So the bridge comes under that, that if you want to study, if you want to consider that bridges having number of supports as a continuous beam, you have to consider it, and we have to find out the shear force and bending moment variations throughout the length of the beam. Then we can know, after that, on those bridges the vehicles can travel, what type of loads we have to consider it again. Is this static? Some of the people will stand parking on the bridges. When they park on that bridge, it is acting as a point load, static load. And when the moving under continuous load, what is the it is the dynamic loads. So these are the various things when we are going to design the bridges or any civil structures. And before going to design civil structures or any bridges, we have to consider the type of load the bridges has to undergo. Now here, consider the fixed beam with uniformly distributed load. The fixed beam with the uniformly distributed load, this is UDL or rectangular load. Type of the beam is a fixed beam. Now what is the SFD? The shear force diagram. Again variation UDL. Positive and again negative. And here how it is varying. Variation, the shape of the bending moment diagram. Next one here, the cantilever beam. The cantilever beam with the point load is applied. Again, the fixed support here. It is a fixed support. Now here, the constant it is. Here it is constant. In this, SFD is varying completely positive. And whereas bending moment is the negative shade, negative bending moment. Negative bending moment means when the load is applied on point P and the fixed beam, it will deform like that bending. The negative bending moment. Negative BM. That's why it is varying. From where it is from here, from free end to fixed end. At the fixed end, it is the maximum, and at the free end, it is 0. A fixed end to free end. Suppose P is acting. The P for a length L. At this fixed point, the maximum bending moment is PL. This PL is negative. Next, another type of beam. Here we can see the UDL is acting on cantilever beam. The type of beam is cantilever beam. uniformly distributed load is acting or rectangular load, the effect of the shear force can be seen in the shear force, variation of the shear force in SFD. It is completely positive. And again, the negative bending moment, the variation of the bending moment is negative. So even though it is negative, but the maximum is where? At the fixed end. At fixed it is maximum, and at the free it is minimum. In shear force and bending moment, if we see the variation of the shear force for the case of this cantilever beam is subjected by this one UDL, the shear force is maximum at fixed end and it is minimum at the left free end, and bending moment is maximum at the fixed end and it is minimum at the free end. Whereas in the case of cantilever beam with point load, cantilever beam with point load is a shear force. The variation of the shear force is constant throughout the length of the beam. But whereas bending moment is varying, this is the bending moment. The bending moment is maximum at a fixed end, and minimum at the free end. Coming here, in the case of fixed beam, when it is subjected, this UDL is acting on the fixed beam, it is maximum at both the ends. Even though it is positive or negative, effect is maximum on both the ends. It is zero at some part of the middle of the beam. So there is no effect of UDL at the middle of the beam. In the case of shear force, the shear force is zero in the middle of the beam and it is maximum at both the ends. And so that even though UDL is acting, the effect of shear force is zero, even the point load also acting on the more, then that effect may be there. So there is no effect of UDL in the middle of the beam. Now the bending moment is maximum for this in the middle, is completely maximum, and it is some value at the extreme conditions bending moment. So these shear force and bending moments considerations are so important in order to design the beams and the structures, civil structures and mechanical structures. In this case, we can see the case 1 is the 1, case 2 and case 3 here. Here in this case, the bending shear force, the variation of the shear force is positive up to half of the length of the beam and negative remaining length of the beam. And the bending moment is maximum at the center of the beam. But here maximum bending moment at the center of the beam and the minimum variation is taking the positive to negative at the center of the beam, shear force. Now, one more important here it is, you can see in the second figure, second case, here simply supported beam. Type of beam is simply supported beam. Type of load is UDL. And shear force in the middle of the beam is low, 0. But the bending moment is maximum. Where shear force is 0, the bending moment is occurring, is maximum bending moment is taking place. Okay. Next one, in the case of the fixed beam, the point load is acting P. If the point load P is acting, again the shear force condition changing the sign, whereas bending moment is maximum at the point. You can see here. So in that manner, we can see the relation between shear force and bending moment. Now, very important is that what are the supports we have seen here? The types of supports. In the case of types of supports, first one is knife edge support. Another one is roller support. Third one is hinged support. And the fourth one is fixed support. These are the 4 types of supports we are going to consider while doing analysis, shear force analysis. Now here, knife edge support I am considering here for a simply supported beam. If we consider in the simply supported beam, I am considering simply supported beam R. Okay. This is knife edge support. Knife edge support representation is triangle, it touching the knife edge. It is a roller support, roller symbol. So the reactions, when the load is applied P, the reactions from knife edge support and roller support is only one reaction we are going to consider for analysis, for calculating the shear force and bending moments. Now it is only one reaction. For this is a knife edge support and here it is roller support. What is this representative? Suppose I am considering again simply supported beam. This is known as hinged support. When the hinged support is there, how many reactions we have to consider for calculating the shear force and bending moment variations? For a hinged support is hinge is connected, it is not exactly outside, the middle of the beam it will be joined. For hinged support, the number of reactions will be 2. One is horizontal, another one is vertical. Whereas for roller support, only one reaction pass through. So the number of reactions, forces are to be considered for hinged support is 2. And whereas for fixed support, it is a fixed symbolism. For a fixed support, load is acting for a cantilever beam. How many reactions are to be considered at a fixed end? There will be 3 reactions. One is vertical, another one is horizontal, and the third one is reaction is moment equilibrium. So there are 3 reactions of forces we have to consider for fixed support, 2 reactions for hinged support, 1 reaction for roller support, and 1 reaction for knife edge support for calculating the shear force variation and bending moment variations. Now, as we have seen before, here it is knife edge support. What is the type of support here? Knife edge support. Here what type of support here? This support is roller support. How many reactions will act for calculating? 1 reaction. Now coming to second case. Here again it is knife edge support and roller support. 1 reaction we have to consider. Here it is a fixed support. The fixed support, there are 2 fixed supports are there. It is a fixed beam. How many reactions? RV1, RV2 and RH1, RH2 and one more M1 and M2. Whatever direction may be. So there are 3. Now, this is a fixed support again in this figure. How many reactions? Again 3. There are 6 reactions are there. RV1, RV2, RH1, RH2, M1 and M2. Now coming to here another one, that is fixed support. Here the fixed, how many reactions? Horizontal 1, vertical 1 reaction, and another reaction is moment equilibrium M1. Okay, here also fixed support. This is RH, RV, and it is RH, and another one is moment. So in that manner, we have to find out the reaction forces And also after using these reactions, we have to calculate the variation of shear force and bending moments throughout the length of the beam. Let me summarize. In this session, we have studied what is the stress strain diagram and what are the variation of the shear force, what is the shear force, what is the bending moment, what is the shear force diagram and bending moment diagrams, and the sign conventions, and the types of beams, types of supports, types of loads, and some of the examples of the shear force variation and the bending moment variations of fixed beam, cantilever beam, and simply supported beams. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.